You can start.
Okay, sir. Yeah. So good morning to all of you. So here we are going to cover fluid mechanics basics, and so in this one, first of all, we are going to look at the syllabus that we are going to cover. So basically, we are going to cover properties of the fluids and fluid statics, fluid kinematics, and then fluid dynamics. Then we have the lambda flow as well as we have turbulent flow also. Then we have the modular theory, dimensional analysis, and then we have fluid machinery also. And of course, the additional syllabus that covers the basics of the compressible fluid flow, right? So all of you, please let me know whether I'm audible or not properly. Okay. 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 So basically here, first of all, we are going to see, the fluid mechanics and fluid machinery. Basically, the weightage is going to be in between, generally varies. Nowadays, from the past 3 years, what we are observing, the weightage are varying from 4 to 6 marks, regarding this fluid mechanics. So what we can do, first of all, we are going to cover, in this session, we are going to cover only fluid properties, that is properties of the fluids, as well as the fluid statics part. And we are going to solve 1 or 2 numerical questions so that you can have the idea about the development of this subject. So properties of the fluid means what are all the properties right? There is a fluids and there is a solids. Suppose if I'll just ask you a very general question, what is the difference between fluids and solids? Then can I have the answer? What is the general difference between the fluids and solids?
Yes, sir. When applying a force, a fluid is continuously deforming. When solid, it's not like that. It will be.
So when I take the fluid element as a solid element, but when I apply the tangential force, it will be continuously deforming, right?
Yes.
But why is it not happening in the solid? Why there is a fixed amount of deformation in the solids? Suppose that this is a
Molecular
solid element.
structures.
Let's suppose we are applying the force, a tangential force, but it is going to defined by let's say deformed by the angle theta, angular deformation theta, or shear deformation. Sometimes we used to say
The
shear angle.
attraction between the molecules is stronger in solids, but in lower in fluids.
What that property, basically we say the whatever you said.
Cohesive force.
Cohesive force. We have some elastic properties in the solid mechanics.
Okay, that is.
See here, the deformations are permanent in the solids, right? That you are agreeing. When we are applying the tangential force, whatever the deformations are happening, that is a fixed amount of deformation is happening just because of the one elastic property, that is modulus of rigidity, right?
Yes.
Because of this elastic property, we say that in solid the amount of deformation is what? Fixed. But in the fluids, we don't have any such properties, right? Here, however small is the shear force, this particular tangential force, it will be continuously deforming. That's the difference between fluid as well as solid. So here the rate of deformation is very important in the fluid, but here amount of deformation, total deformation is important, not the rate at which it is deforming. Understanding or not?
Yes.
Right. So in the fluid mechanics basics, we are going to cover the fluid properties. So what are all the fluid properties we have? We have basically the density. Yes or no? What else we
Yes,
have
sir.
property? What else property we have? We have the density, we have a specific gravity. Yes or no?
Yes, sir. Specific heat, viscosities,
Specific gravity. Then weight density
thermal
also we have.
conductivity.
Yeah, of course, we have many properties, but as far as the fluid mechanics concerned, I'm asking, right? So density, specific gravity, weight density, these are all what? Properties, right? So coming to the fluid statics, in the fluid statics, we are basically going to cover the pressure measurement, right? How the static pressure can be measured. What is the difference between absolute pressure and gauge pressure, right? What is the total pressure? Understanding or not? And then in the fluid kinematics, we are going to cover the velocity and acceleration analysis of the particular fluid element, right? Without understanding the causing or basically the reason for that particular velocity and acceleration, you know that the reason, the force, right? Yes or no? Whenever any body is moving or doing linear motion, the force is responsible. But whenever any body is rotating, there is a torque that is responsible. But we are not going to cover those things in the fluid kinematics. Those things will be covered in the fluid dynamics, right? Understanding or not? Velocity and acceleration part we are going to cover in this fluid kinematics. In the fluid dynamics, we are going to cover what? Forces, right? If I just say only forces, that will not be signifying this subject called fluid mechanics. Here we have many forces, right? We have the viscous force, surface tension force, gravity force, right? Elastic force, inertia force. Understanding or not? Yes or no, guys?
Yes, sir.
And then we are going to cover the types of flow also. In fluid mechanics, we have many types of flow. Basically, we categorize in three types: laminar flow, transition flow, and the what? Turbulent flow, right? So basically, we are going to cover laminar flow as well as we are going to cover this turbulent flow also, right? And then we are going to cover the boundary layer theory. Then we are going to cover this boundary layer theory also, right? Then we are going to cover the dimension analysis as well as we are going to cover the fluid machinery also. Right. So these are the overview of this fluid mechanics. So generally, what we are observing for the past 3 years, that the 2 mark question generally varies from, in count 2 to 3. So you can say 6 marks. 1 mark question can be, theoretical point of view, 2 questions. So you can say 8 marks. So exactly, I cannot say that this particular weightage will be given to this particular subject in the next year, but it will vary from 6 to 9 marks, right? In a broad sense. Yes or no, guys?
Okay.
Now, so all of you have noted down?
Yes, sir.
Yes. So basically, we are going to cover the properties of the fluids, and the objective will be, when we are going to about to finish this particular properties of the fluids, then we should have the basic knowledge of the properties of the fluids, and we should understand the concept of continuum, right? And we should have the working knowledge of the viscosity as well as what are all the effects of the viscosity, right? Now, note down the property. Any characteristic of a system is called as property. Now, the property can be extensive and can be intensive also. Now, what is the meaning of intensive properties? Intensive properties are those properties which are of the independent of the mass, which does not depend on the mass, right? So if I say temperature, pressure, and density, they will not depend on the mass, right? What example I can say? Just observe very carefully. Let's suppose that I have the room, right? Here we have the air molecules, suppose that, right? Atmosphere air molecules are there. But suddenly what I did, I just divided this room into 2 segments, equal segment. Whatever the before, let's say that pressure and temperatures are there, P and T, After dividing, we cannot say it's a P by 2, T by 2. It will be P and T only. Understanding or not? So even though the volume has been divided, even though the mass has been divided, it does not depend on the mass. That's why we say pressure and temperature are the intensive properties, right?
Okay.
Yes or no? And of course, we have the density also. The density, what is the meaning of density? It's a ratio of mass by volume, right? Mass is extensive extensive thing, and volume is also what? Extensive, because that they depends on the what? Mass. That depends on what? Size or the extent of the system. What are all the extensive property we have? Total mass, total
Sir, your
volume.
voice is low. It's not properly.
Is it fine now?
No, sir.
Still low?
Still low, yes.
Just wait. Hello, hello.
Now also it's low, sir.
Huh? Now also? Hello, hello. I'm audible? Okay, fine. So just note down the intensive property as well as extensive property. So intensive property basically are the properties that independent of the mass of the system, that does not depend on the size of the system, all I can say. But extensive property means those will depend on what? Size as well as mass of the system, right? Total mass, total volume, total momentum. What is the momentum? M into V. Mass into velocity, that is what? Total momentum. But that is also depend on what? Mass, right? These are the examples of the what? Extensive property, no doubt. If I say specific enthalpy, whether it's an intensive property or extensive property, if I just ask you the specific enthalpy, whether it is an extensive property or intensive property, yes, it is an intensive property. Why it is an intensive property? Because specific word. Specific means anything divided by mass. That will be what? Specific enthalpy, right? Enthalpy unit is what? Kilojoule. If I just say divided by kg, that will be the unit of specific enthalpy. Understanding or not?
Yes, sir.
Yes or no, guys? Now, if I just ask you, what we can say, the kinetic energy and the potential energy, whether they are extensive properties or intensive properties. Whether they are extensive property or intensive property, potential energy as well as kinetic energy. We say potential energy mgh, we say kinetic energy as half of mv square. They depends on what? Mass. So it's a what? It's also what? Extensive property. Note down. They are extensive property. right? Is it done, all of you? Now, note down the next concept, the concept of continuum. The concept of continuum. So anybody have any idea about this concept of continuum? Maybe you are very well known, aware of this particular fact, but after today's discussion, you will be surprised to see many things about concept of continuum. As of now, if I just ask you in one word, anybody know about this thing? Treating the matter continuous, right? Treating the mass distribution as a continuous, in a continuous fashion, right? So basically, the concept of continuum is saying that the matter is made up of so many atoms, and the atoms are widely spaced in the particular gas phase. The matter is made up of atoms that are widely spaced in the gas phase, yet it is very convenient to disregard the atomic nature of the substance and view it as a continuous or homogeneous matter with no holes. Means that means what? We are treating this as what? Continuous matter. But what is the significance of these particular assumptions? Of course, whatever we are talking, that is that is a perfect assumptions. That is not actual thing. Whatever we are discussing, it's just an assumption. If that is the assumption, then what is the reality? What is the actual thing? Suppose that in a particular space, we have so many molecules, air molecules, right? In a particular space, let's suppose that we have air molecules. In a particular space, let's suppose that we have air molecules. This air molecules, my dear friend, what will happen? Can you see the gap between the air molecules? Can you see the gap? Can you see the empty space between the molecules as of now? Tell me, guys. Yes. When you can see the gap or empty space between these molecules, right? Whatever I want to say that this gap is what? Empty space. When you see that very clearly from your own eyes that there is empty space between the molecules, then how can you say that the matter is continuous? That is a completely assumption what we are observing as of now. Whatever the concept of continuum is there, that is just an assumption. That is not the actual reality, right? But still, we are treating this assumption to be very good, accurately, correctly, because whatever the empty spaces are there, that is in the scale of nanometer. When you take the when you take your mobile, when you zoom it, 10x or 20x or 30x, still you can't see that particular gap between the molecules. They are in the nanometer, my dear friend, right? They are in the nanometer. You cannot observe. Very, 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 very small gap is there, right? That you cannot see at all. That's why it is very good, very convenient to assume the matter to be what? Continuous, right? If I just talk about the solid, solid what we are observing, whatever the matters are there, they are in the continuous fashion because they are closely packed. Whatever the gap is there, that you cannot see at all. In solid, that is very, very convenient, very accurately, whatever the assumption is there, concept of continuum is valid. But what about the fluid? Why it is differing as compared to the solid? In the fluid, what happens when you heat it, when you just apply some pressure, temperature, what happens? The molecular behavior got changes. Whatever the gas particles are there, they are trying to basically widening their spaces. They are trying to change their molecular momentum. They will just try to collide with each other, and they will what? Occupy spaces. A lot of things are happening with the fluid as compared to the solid. In solid, that does not going to happen so much thing because they are closely packed. In the material science, you are going to study what is the meaning of closely packed structure. But in the fluid, that does not happen so, right? But still, we are treating this in the fluid also. We are treating the matter of the concept of continuum to be valid. Now, tell me one reason. What is a very good achievement we can just get it out of it when we treat the matter to be continuous like this? When we say the gap is very, very small, when we say the matter can be treated as continuous, what is the achievement we can get it? Tell me. The matter is continuous. The matter is continuous. Apart from simple calculation, any other reason you have? The matter is continuous. I'm saying that the matter is continuous. But how your calculation is very, very simple, got simple. Any other reason you have? What is the reason that you're saying that whatever the calculation is there, that will become simple? What's the reason behind that? I just want to know the reason for that. But I'm saying that the matter can be treated as continuous. It means that you can apply whatever the laws are there, whatever the governing laws are there. See, neglecting nanoparticle, no. See, whatever the Newton's second law, whatever the Newton's third law, whatever the laws are there, right? Whatever the laws you have studied in the engineering mechanics, you are applying to the particle, right? Force is equal to ma. Net force, whatever you are applying, is equal to what? Mass into acceleration. Suppose that. Whatever the u is equal to, suppose that s is equal to ut plus half at square. Whatever the equations of the Newtons you are applying to the single particles, right? When you treat the matter to be continuous, that means you can consider all the fluid particle as single entity, like this. Single entity. When you consider this whole particle, system of the particles, suppose that in this one 10 to the power 6 particles are there. I'm just saying that maybe 10 lakhs particles are there. But when the gap is very, very small, you can treat this complete fluid particle as single entity. Now, in this case, what will happen when you assume that single entity? Now you can apply the Newton's second law or whatever the all the laws are there, all the laws that exist actually for the engineering mechanics, that you can apply very conveniently, very easily. Otherwise, what will happen? Assume the situation, or just imagine the situation when you just don't assume that the concept of continuum to be not valid. When the concept of continuum is not valid, then you can see the gap. When you see the gap, you cannot directly treat this complete particle as single entity. Now, in that case, what you need to do? No, single particle, apply whatever the velocity is there, u plus at. For this also, apply v is equal to u plus at. For this also, apply v. Suppose that you want to find the velocity of the complete system, then what you have to do? You have to follow Lagrangian approach. That means we have to follow single particle, and that is going to take a lot of amount of time, lot of resources is going to take, and lot of amount of what? Mathematical calculation will also be involved. Now you got to know why the concept of continuum is very, very important thing. Tell me this. You might have studied this particular topic, but you never getting the practical real meaning of what the meaning of concept of continuum, right? That is the meaning of concept of continuum, treating the matter to be continuous. It's not like that we are treating the matter to be continuous. That's a very, very simple thing. One of the very simple thing is that when we treat the matter to be continuous, we can treat this particular whole number of particles, whatever the number of particles will be there, can be considered as single entity. And now whatever the laws are there, directly we can apply, right? Whatever the Bernoulli's equation is there, whatever anything is there, we can directly apply. Even our fluid mechanics depends on Eulerian approach. I will tell you what is the meaning of Eulerian approach as well as Lagrangian approach. We are not following any Lagrangian approach. Whatever the engineering mechanics you are observing single particle. Let's suppose that block is there. You are applying the forces and you are finding the velocity and acceleration for this particular block. But this block is considered as single entity. But in the fluid mechanics, we are not observing. Suppose that in a particular pipe, the flow is happening. We are not observing single particle. We are observing a bulk particle, whatever the number of particles that is passing through a one particular segment. And that is what the concept of Eulerian approach. We are not observing any Lagrangian approach. There is a two types of approach that we are going to cover in the fluid mechanics. Lagrangian approach, that is for the research purpose. We are going to follow single particle, and that is going to take a lot of amount of time, right? Eulerian approach means we are going to treat the number of fluid particle as a single entity that is passing through a particular segment in a particular pipe or whatever the flow section is there. Yes or no, guys? Tell me, guys. And that is what happening in the thermodynamics also, right? To save the time, we follow Eulerian approach. Yes or no? Right. So note it down. Basically, to have the development of this concept of continuum is valid. For validity of this concept of continuum, we define one number. That number we call Knutson number. Just note down the Knutson number. It is defined as lambda by L. Sir, what is the meaning of Knutson number? Basically, Knutson number is define the validity of the concept of continuum. When Knutson number is less than 0.01, then we say the concept of continuum is valid. Then continuum concept is valid. When the Knutson number is less than 0.01, then only we say that the concept of continuum is valid. Otherwise, it is not valid. What is the lambda? Mean free path. Note down. Mean free path. What is the meaning of mean free path? The average distance traveled by the fluid particles before colliding with the other particles, right? This gap is lambda. What is the meaning of L? System length. Note down, system length. What is the system length? This is the system length. Well, lambda, the distance between the fluid particles or gas particles or liquid particles are very small as compared to the system length, then we can assume that the concept of continuum to be valid. In that case, what is the meaning of this? Well, lambda is very lesser than this particular system length, then we can assume that the matter to be continuous. No doubt. This is very important. Till now, we are expecting that in GATE examination, this question will come about the Knutson number, but they are never touch this particular part. So note down, this is a very important. This concept is not only basically in the fluid mechanics, as it is very important in the thermodynamics also, right? There also we are treating the matter to be continuous. We cannot have the luxury of spaces between the fluid particles, right? Done. Is it done, all of you? All of you have noted down? Perfect. Now note down some of the fluid properties. Like we have density. Density is defined just mass per unit volume. And of course, a reciprocal, you know that the specific volume. This specific volume will be very useful in, pure substance. This will be very useful in pure substance. meter cube per kg, right? So note down density basically defined as mass per unit volume. The reciprocal of the density will be defined as specific volume, right? See, these are the very important thing, but some of you might be thinking that's a density. We already know that, right? But it is a very important, my dear friend. As for fluid mechanics concerned, the density is very important. A lot of things will depend on the density. Then note down the specific gravity. Specific gravity, we also say relative density. It is defined as the density of the substance, any substance, to the density of the some standard substance at a particular specific temperature. When we say when we define the specific gravity for liquid, then what is the standard fluid? What is the standard fluid? Water. When we define a specific gravity of the gases, then what we are going to have? Standard fluid, standard gases. What we can have the standard fluid? Air. Very good. Note down, very important. Sometime in some of the textbook you will find rho of the liquid into G divided by rho of water into G, right? That rho into G, this particular term we define as weight density. And of course, G will cancel out, so you automatically will be getting this sum on this thing only. So sometime we used to say the specific gravity in terms of weight density of the liquid to the weight density of the standard fluid. So do not confuse, sir, why there is a weight density, but you said only density, right? So G and G will cancel out, so you'll be getting what? Weight density, which is just defined by gamma. What is the unit? Newton per meter cube. Note down, very important. I think done, right? Note down the next thing. So specific gravity is a dimensionless quantity. However, in SI unit, the numerical value of the specific gravity is exactly equal to its density, right? That is in the gram per centimeter cube or kilogram per liter or kilogram per meter cube. Specific weight we also call weight density. Note down specific weight or weight density. Or weight density. Both are same thing. We just say rho into G. And what is the unit? Newton per meter cube. Now note down the density of the ideal gas. Ideal gas. This is the ideal gas equation we have. PV equal to MRT. But if I just say P equal to M by V into RT, so we are going to get P is equal to rho RT. But equation is not important. All of you might be knowing the equation. But the main thing is what? P is what? Absolute pressure. It's not a gauge pressure. It's not a local pressure. It's an absolute pressure. Please note down. Very important. Done? Is it done? No. Note down the term viscosity. It's also fluid property. But what is so special about the viscosity? That is also very important thing, right? whenever the two bodies, whenever they will be in contact, let's suppose this body is there, body number 1, and the ground surface, which is fixed one, I'm assuming to be body number 2. When I just move the block by applying some forces, what will happen? There is some kind of roughness might be there on the body number 2. Because of the roughness, there might be friction forces that will be acting. Yes or no, guys? There might be some friction forces that is going to acting in this opposite direction. Friction forces. And that will oppose the motion of the body number 1. Whatever the friction force you are observing in the solid mechanics, in the fluid mechanics, whenever the fluid elements are there, let's suppose that I would say the fluid layer 1, this is a fluid layer number 1, and let's suppose that this is a fluid layer number 2. When I move this particular fluid layer number 1 with some velocity v, what will happen? There is some kind of what? Let's suppose that the fluid particle, the gap is very, very small. The gap, you can neglect it. Even though I mentioned the gap, but you can neglect the gap. Whenever the fluid particle, fluid layer number 1 is just moving with respect to fluid layer number 2, what will happen? The fluid layer 2 will try to oppose the motion of the fluid layer 1. Why? Just because of the property called as viscosity, right? Note down. When the two solid bodies, they will be in contact and they will be moving related to each other, a friction force will be developed at the contact surface in the direction opposite to the motion. This situation is very similar when the fluid moves related to the solid, or when the two fluids move related to each other. The properties of that represent the internal resistance force of the fluid to the motion is called as what? Viscosity. Note down. Very, very important. Whenever the two fluid layers are moving with respect to each other, they will try to oppose the motion of individual. Then this internal resistance behavior or the property of the fluid layer will be defined by what? One property. That property is called as what? Viscosity. Right? Suppose that there is a plate. On that particular flat plate, the fluid particle is moving with some velocity u infinity. Right? With some velocity u infinity. What will happen? This fluid, this solid flat plate is what? Fixed one. This is fixed one. So whenever the fluid particle, first fluid particle, let's suppose that this is made up of so many layers. I'm assuming these are made up of 5 layers. First, second, third, fourth, fifth. 5 fluid layers are there that is coming in contact with a solid plate. The moment they will be coming in contact with the flat plate, the first fluid layer will be coming to the what? Rest condition. Because of what? No slip condition. You will come to know in the Modulus theory what is the meaning of no slip condition, right? The first fluid particle will be what? Absolutely having 0 velocity. What about the second layer? Second layer is going to have some kind of velocity, but not exactly as u infinity. The third is also going to have the velocity, but not exactly the same as the u infinity. The fourth also going to have, the fifth is going to what? Something like this. The fifth layer is going to assume the velocity 0.99 times of u infinity. Because of this, my dear friend, viscosity, because of the property of the fluid viscosity, the development of the boundary layer is going to be started like this. So if somebody will ask you what is the reason of the boundary layer formation, you must say no slip condition as well as viscosity. Understanding or not? Why the development of the boundary layer has been forming? Is that clear? Tell me, guys. How the formation of the boundary layer is happening. I just said in a particular 5 minutes of the segment, but you must be understanding why the boundary layer formation has been taking place. But when we are going to deal with the boundary layer, we are just going to explore like anything, right? I'm just giving the glimpse or the highlights of what we can have the achievement in the boundary layer theory. Just sort, I would say that the viscosity. one of the major role that is playing the development of the boundary layer formation is what? Viscosity. Note down. Why the fluid layers are having different viscosity? Just different velocity, just because of the property. That property is called as what? Viscosity. Note down. Viscosity, we will say directly say dynamic viscosity. Because if I say viscosity, we have the two types of viscosity, dynamic viscosity as well as kinematic viscosity. Then, is it done? Now, note down the Newton's law of viscosity. Note down Newton's law of viscosity. What is the Newton's law of viscosity? According to Newton's law of viscosity, the shear stress is directly proportional to velocity gradient. When I remove the proportionality, I will be getting one constant, mu into du by dy, and that constant is called as dynamic viscosity. Note down. That particular constant is called as dynamic viscosity. Now you can see the flat plate. This is a fixed one, and upper plate is what? Moving. Upper plate is what? Moving with some velocity v. But in between, whatever the fluid layers are there, they are having what? Different velocity. As you can observe, they are having what? Different velocity. Just because of the fluid property called as viscosity. Right? Whatever the du by dy is there, that is the slope. Whatever the du by dy is there, that is a slope that we can find by the velocity profile. This theta is what? Du by dy. Right? But the gap is very small. Note down one note point. When gap is small, then we can assume du by dy as u by y. When the gap is very small, then we can assume that gap to be what? U by y, or we can just assume that whatever the gap is there. Let's suppose that gap is L. Let's suppose that gap is what? L. Then we can assume u by L. Right? When the gap is very small, then we can assume that linear profile. And in that case, you can just find by similar triangle u infinity by L directly, theta value. Yes or no, guys? All of your understanding? All of your understanding? In what condition we can assume the gap to be linear one? When the gap is very small, then we can assume the velocity profile to be linear one, right? You can also see that. It's not that there is a rocket science, you can see that. When the gap is very small, even though velocity profile is parabola, but you can treat it like a linear one because gap is very small. When the gap is large, then only we can see this complete velocity profile to be parabola like this. I'm not saying that the velocity profile always parabola. It can be linear also, right? But the velocity profile can be uniform also. When the velocity profile in linear one, then du by dy will be what? Then du by dy will be 0 in that case. Then what will happen? The shear stress will be 0. The shear stress will be 0. Note down, this type of fluid we call ideal fluid. Whatever the fluid layer is there in this one, now we can say that this condition is what? Ideal fluid. Note down. Very important, ideal fluid. So ideal fluid never exists, but we can have the assumption as ideal fluid in which we have no viscosity, nothing is there. Then so we have the ideal fluid, we have ideal flow also, right? All this detail will be explored in the course, right? Whatever the doubt you might be having about the ideal fluid, ideal flows, or what is the difference? Yes, there is a difference between ideal fluid and ideal flow. There is a difference between ideal fluid as well as ideal flow, right? But for that, you need to be patient, and for that, you need to wait for the course to be started, right? Done. Now, of course, this slide I already covered. The fluids for which the rate of deformation is proportional to the shear stress are called as Newtonian fluids. Just note down one point. The fluids for which the rate of deformation is proportional to the shear stress. That means shear stress will be directly proportional to du by dy. That type of fluid we call Newtonian fluids. But for the fluids for which the rate of shear stress, for which the shear stress is not proportional to the what we say that directly proportional to the rate of deformation, that we say non-Newtonian fluids. Non-Newtonian fluids. Right? Something like this. Tau will be equal to k times of du by dy to the power n. It's not directly proportional, right? To the power 1. So whatever the example of the Newtonian fluid is what? What are all the examples we have? Tell me, guys. What are all the examples of the Newtonian fluids? Air, petrol, diesel, water, etc. These are all the examples of the what? Newtonian fluids. What are all the examples of the non-Newtonian fluids? If I just ask, what are all the examples of the non-Newtonian fluids? Tell me, guys. Paints, blood, etc. Yes or no? Yes or no, guys? Okay. So just note on this particular graph also. This is a graph between the shear stress as well as rate of deformation. This is a graph between the shear stress as well as the rate of deformation. So basically in this graph, what we are observing, through this graph, what you are observing, the shear stress versus du by dy. I said that the rate of deformation is what? Directly proportional to the shear stress, right? But of course, this is directly proportional. It's not a parabola proportional. Whatever the directly proportional relation is there, that is also showing to you. But who is having more viscosity, if I just ask you, among oil, water, and all? Because you know that whatever the slope you will find, theta, the slope is what? Directly viscosity. d tau by du by dy. So which is having more slope? Theta of oil, theta of water, and this is theta of air. So what I can observe, theta of oil is more than theta of water, more than theta of what? Air. So viscosity of oil is more than viscosity of water than viscosity of the air. Please note down. Very, very important. Just by observing the graph between the shear stress as well as rate of deformation. Why we are calling rate of deformation? Because see, what is the unit of du by dy? Meter per second, meter. This will cancel out 1 upon second. That's why we are saying rate of deformation. Done, all of you? Is it done? Perfect. Note on the kinematic viscosity. Kinematic viscosity, basically, it's a ratio of the dynamic viscosity to the density. It's a ratio of the dynamic viscosity to the density. That is called as what? kinematic viscosity. What is the unit of the viscosity? Pascal second. Pascal second. Why Pascal second? Tau will be equal to mu into du by dy. What is the unit of tau? Newton per meter square. 1 upon second. So mu is what? Newton second per meter square. What is the Newton per meter square? Pascal. That's why I'm saying that Pascal second. That's why I'm saying what? Pascal second. Right? What is the unit of the kinematic viscosity? Meter square per second. Right? So if I just say SI unit, meter square per second, but if I just ask you CGS unit, what is the CGS unit? Stoke. 1 stoke is what? 10 to the power minus 4. 1 stoke, please note down, 10 power minus 4 meter square per second. Similarly, what we have the CGS unit of the dynamic viscosity, anybody know? 1 poise equal to 0.1 Pascal second. Note down. Poise is a unit of CGS unit of what? Poise is a CGS unit of the what? Dynamic viscosity. Please note down. Done, all of you? Is it done? Very quickly we can have, I'm going to just take 10 to 12 minutes more, and I'm going to cover the fluid statics, actually, pressure measurement, so that we can solve at least one numerical, so that we can wind up this session after that. Done, all of you? Is it done? Okay. Note on the fluid statics. In the fluid statics, basically what we are going to cover, fluid statics, we are going to cover basically pressure measurements. What is the meaning of pressure? Pressure is a compressive force or tensile force. I'm just asking one question. If I just say pressure force, it's a compressive force or tension force onto the fluid element. Whatever the pressure forces are acting, they are in nature compressive nature or tensile in nature. Tell me, guys. Whatever the pressure forces are there, they are in nature. Basically, they are in the what? Tensile in nature or compressive nature. By default, what we say? Tell me, guys. Whether it is a compressive one or tension one. Basically, what is the meaning of tension and compression? In solid mechanics, you might have observed whenever we try to pull this body with the force F, then we say it's a tensile force. But whenever we try to compress it, we say it's a compressive force. What is the nature of the pressure force? Compression or tension? Tell me, guys. It's a compression, right? Yes or no, guys? It's a compressive in nature. All of you are understanding or not? Right. So pressure is defined as the normal force exerted by the fluid per unit area. We say it's a pressure. So what are all the units we have? We have many units. Just note down 1 bar. 1 bar is equal to 10 to the power 5 Pascal. We also say 0.1 megapascal. We also say 100 kilopascal. 1 atmosphere pressure will be what? 101.325 kilopascal or 1.0132 bars. Please note down, do not confuse with the bar, as well as don't say 1 bar equal to 1 atmosphere. It's incorrect. 1 atmosphere will be equal to 1.01325 bars, right? And after that, we are going to have what are the difference between atmosphere pressure, gauge pressure, as well as absolute pressure. Whenever remember actual pressure, suppose that you are sitting in a room, suppose that in your room, suppose if I'll just ask you At the point at which you are sitting right now, what is the pressure? Then you must say absolute pressure. You should not say gauge pressure or atmospheric pressure. You must be defined by the term called absolute pressure. Whatever the actual pressure is given, actual pressure will also be given by, always be given by what? Actual pressure will always be given by absolute one. Not the what we say atmosphere pressure, not by the gauge pressure, right? Done, all of you? Note down this particular diagram. This is the reference point. This is what we have the reference point. From the reference point, suppose that atmosphere pressure is this much. After that, suppose that we have the gauge pressure. Now, if I'll ask you what is the total pressure, you must say total pressure is what? Absolute pressure. And what is this? Atmosphere pressure plus gauge pressure. That is the absolute pressure, right? Sometime what will happen? The atmosphere pressure will be more, but what we say absolute pressure is less. In which condition? When we have the vacuum. When we have the vacuum, in that case, absolute pressure will be lesser than atmosphere pressure. And that we can find by this particular thing, atmosphere pressure minus of vacuum pressure, as you can see. Actually, atmosphere pressure is what? Fixed one only. That cannot be changed. Whole universe in your room, atmosphere pressure is what? Fixed one. Now the gauge pressure can be above or can be below that atmosphere pressure. But if it is below that, then what will happen? The total pressure from the reference point, this is my reference point. Whatever the 0 point is there, that is my reference point. From the 0 level, we are measuring each and everything. Right? This is the formula for this one, and for this one, this is the formula. Done? Is it done? No. Just note down. Anybody know about the hydrostatic law? Anybody know about the hydrostatic law? Anybody know about the hydrostatic law? Hydrostatic law is saying that the pressure in a liquid, which are at the rest condition, is going to vary, is going to increases linearly with the depth from the free surface. That means the pressure will be directly proportional to H. Pressure will be equal to what? Rho G into H. That is what the hydrostatic law. When you are moving downward from the free surface, the pressure is keep on increasing. The pressure will be keep on increasing like this. And how it is varying? It is going to vary linearly until unless the density of the fluid will going to change. Right? Let's suppose that all the depth, the fluid layer is what? Constant. The density is constant. G is constant. So can I say directly that P is directly proportional to H? Yes or no, guys? Tell me, guys. But whatever the pressure is equal to rho G H, whatever we are calculating, that is not a total pressure. At the free surface, there might be some atmospheric pressure. At this point, suppose that if I'll just ask you, at this point, if I suppose asking you how to find the total pressure. At this point, if I just ask you what is the total pressure, what do you say? Sir, atmospheric pressure plus rho GH. That is what the absolute pressure. Understanding or not? Tell me, guys. All of your understanding? At the point number 1, if I just ask you what is the total pressure from the depth of H, then what you will say? Atmosphere pressure plus rho GH, gauge pressure. Yes or no, guys? Tell me, guys. Yes or no? Right. Note down. That is what we are observing from the hydrostatic law. Now, you know that what we are observing from the hydrostatic law, the pressure is directly proportional to H, right? That does not depend on the size of the container and whatever the depth of the sorry, it depends on the depth of the container, but it does not depend on the size or cross section of the container. As you can observe from the figure, the point number A, point number B, let me just change the color. Point number A, point number B, point number C, point number D, point number E, point number F, G, H, whatever the no G till G point. What you are observing, the depth is constant. At all the point, depth is constant. That's why we are saying pressure at point A, pressure at point B, C, D, till G point, the pressure is going to be same. The pressure is going to be same, and that is equal to what? Atmospheric pressure plus rho G H, because H is constant. That does not depend on the size of the container or no shape of the container. It is rectangle one, it is somewhat triangle one, it is what curvature one, something like this. But that does not depends on the what? The shape or the cross section. It only depends on the vertical distance from the free surface. That's it. Right. But if I just ask you at the point H as well as point I, the pressure is not going to be same. Why? Anybody know the reason? If I just ask you the pressure at point H and the pressure at point I, forget about the atmospheric pressure. Suppose that atmospheric pressure is 0. But what about the pressure at point H? What you will say? Rho of water G into, suppose that the height is what? H1 and this height is what? H2. H1 plus mercury height, rho into mercury, G into H of mercury is what? H2. This will be the pressure at H. But what about the pressure at I? What about the pressure at I? Let's suppose that same height is there, or what we can observe, rho of water, G into, suppose total height is what? H1 plus H2. H1 plus H2. Suppose that. Now whether they are different or same? Different, right? Until unless rho and G are constant, that pressure will be directly proportional to H. But the moment rho or the density of the fluid will change, the pressure will also change. Yes or no? Yes or no, guys? All of you are following me? Correct. All of you have noted down? Just last 2 minutes I'm going to take, and I'm going to solve a numerical that is a very good numerical, right? Some of you might be thinking that these are the very simple thing, but this is not a very simple thing. You will come to know very soon. Done? Can I move to the last slides? Is it done? All of you have noted down? Okay. Just note down the last topic, hydrostatic forces on a submerged plane surface. Whenever any body is there, which are just submerged in a liquid, any bodies there which are submerged, let's suppose that there is a boat which are submerged in a particular liquid. What will happen? The liquid will observe, liquid will be what? Applying some kind of pressure force onto this particular object. But how to calculate that? How to calculate that? Just note down the formula, rho G into H bar into A. I will explain you each and everything, but just note down as of now. The pressure force can be calculated, the hydrostatic pressure force. The hydrostatic pressure force can be calculated on a submerged plane surface as rho G H bar into A. H bar is what? The centroidal distance from the free surface of the body. The centroidal distance of a body from a free surface. The centroidal distance of a body from a free surface, that is called as H bar. A is what? Cross-sectional area. of a particular object. Whatever the cross-sectional area will be there, that is called as A. Note down, very, very important. But a very good observation will be there. Sir, when we are observing the atmospheric pressure force, when we are observing, sir, whenever any body is there, just suppose that this is the container. Suppose that we dipped any particular vertical plate. Suppose we are finding the pressure force. Do we need to consider atmospheric pressure force also? Suppose this is a container. This is the container I'm having. This side we are just we have the liquid which is filled in the container. The liquid which is filled in the particular container, like this. Because of the liquid is observed to have some kind of pressure force onto the right side of the wall. It's like this. This is the right side of the wall. This is the right side of the wall, and the pressure force is going to exert something like this. Now tell me, do we need to consider, see, liquid pressure force we are observing, but do we need to consider any atmospheric pressure force? Tell me, guys. Do we need to consider any atmospheric pressure force apart from the liquid force? Yes. Tell me, guys. Do we need to consider, apart from the liquid force, pressure force, do we need to consider atmospheric pressure force also? No, my dear friend. Try to observe. Suppose that we have the wall. Suppose we have the wall, something like this, and we are observing the liquid pressure force on this particular wall. My dear friend, atmospheric pressure will be there inside as well as outside, and this part will cancel out. So that will be equal to what? This symbol. When we just subtract it, then what we are observing? The pressure to be what? Equal to rho gh only. Are you getting my point, what I'm saying? Atmospheric pressure force will be acting from both the sides, from this also and from this also. So this will cancel out. So only we have what? Liquid pressure force. Understanding or not? Try to think and tell. Right? Suppose you are not observing this particular segment, you can just observe by this particular numerical. Try to have attempt of this numerical. See, these are the very, very simple thing, but we just whenever we are going to explore the syllabus, that is my challenge, that we are going to solve n number of problem from, and not only from this particular subject, we are going to solve number of problem from the NPTEL, right? Whatever the question they are asking the GATE examination, directly they are taking from the NPTEL video, NPTEL courses only. That question we are going to cover. Also, we are going to cover the fluid mechanics question from the engineering science, that is XC paper, so that the no question can be left out. Not only from that, we are going to solve aerospace question also, apart from the mechanical, so that wide variety of the question we could have in the particular session. One of the question I have taken from the aerospace, I find it very good question, right? Because some of you might be thinking that whatever the hydrostatic pressure force is there, that we already covered in the BTech also, and we can solve number of problem based on that particular topic, but it's not like that. Just think of this question. A cubical tank basically it is filled with the water up to the height of what? 1 meter. Up to the height of 1 meter, it is going to fill with the water. Not complete height, only half of the height is filled with the water. Only the height 1 meter. What is the total height? The total height is what? 2 meter. What is the total length? 2 meter. And this is also what? 2 meter. What we need to find? The net hydrostatic force on the side of face of the tank. Side face means this face. Side face means this face. On the side face of the tank, we need to find the total hydrostatic force. Just tell me, my dear friend. Just tell me, my dear friend, whether any hydrostatic force will be acting on the upper part of the tank, this part. Let me color by some different color, this part. This green color will be facing some kind of pressure force or not. Whatever the above 1 meter is there of the tank will be facing any kind of pressure force, because there is no liquid. If there is no liquid, there will not be any hydrostatic force. Understanding or not? Tell me, guys. When there is no liquid, there will not be any hydrostatic force. All the hydrostatic force will be acting in the downside of the plate. Yes or no, guys? All the hydrostatic force will be acting on to this particular side, like this. Something like this, right? Now, some of you might be thinking, sir, what about the atmospheric pressure force? Here also atmosphere, and from outside also there is atmosphere. Here also atmosphere, from outside also there is atmosphere pressure force. So whatever the pressure force will be due to air, that will be cancelled out. That's why the trick they played. What the trick they played? The net hydrostatic force on the side face of the tank due to air as well as water, so that you will confuse. See, whatever the net hydrostatic pressure force will be there, that you can easily calculate. That you can easily calculate, my dear friend, by the formula. What is the formula you have? Rho G H bar into A. What I said, my dear friend? Rho into G. What is the H bar? What is the H bar? H bar is nothing but the centroidal distance of the particular part, the centroidal distance of the part from the free surface. What is the centroidal distance? What is the centroidal distance? Can I say 0.5 meter? And what is the cross-sectional area? What is the cross-sectional area? 1 meter into 2 meter, right? That will be the cross-sectional area or not? Tell me, guys. So what we need to find? We need to find in kilonewton. So rho is what? Suppose 9.81. 0.5 into 2 is what? 1. So directly we are getting what? 9.81 kilonewton. That is the answer. Some of you who is not aware of the fact of this particular concept, suppose some of you who is not aware of this particular concept, what the answer they will tick, they are going to tick the option called, 9.81 plus atmospheric pressure into area, and they are going to get the wrong answer. Understanding or not? They are going to click 209.81 kilonewton, but that is incorrect. All of you understanding what actually I'm talking about? Tell me, guys. All of you are understanding what actually we are talking about?
Yes, sir.
Right? So it's actually
I have a small doubt, sir.
that is a wordful. Yes.
Density you mentioned, I think it is a 1, but they are mentioned water density as 1000 kg per meter cube.
Yeah, but we are calculating in kilonewton, right? So automatically that will be cancelled
So
out.
it will be 1
I'm
Newton.
taking in kilonewton. Yes, yes.
Okay, sir. Okay.
Right. The motive behind this putting this question is that you must understand each and every point. Even though they mention forcefully that they want you to commit the mistake, that's why they mention side face of the tank. Not only this side, you can just calculate on this side also. But any side face of the tank, you need to calculate the hydrostatic pressure force because of the air and because of the water. But remember that whenever the question will be coming, you need to consider only water pressure force, not the air pressure force, because that will be cancelled out from the both sides. You can't say you are sitting in a room, the atmospheric pressure force is acting in your room only, not outside of your room. It's not like that. Whatever the wall of your room is there, that is facing the atmospheric pressure force from inside as well as outside. Yes or no?
Yes.
Right. So that's a very important question. A lot of students committed the mistake during those years as 209.81 kilonewton. That is absolutely incorrect. And of course, that is not 1 mark, 2 mark question. So a lot of particular this concept will be explored when we discuss in detail about in the particular fluid mechanics course, right? Just a glimpse of this particular thing that we discuss in 1.5 hour session. Only the part I can say that only 0.1% of the fluid mechanics that we covered. A lot of things are remains left, and that will be covered when we start our discussion on the fluid mechanics basics, right?
Okay.
Yes or no, guys?
Yes, sir.
So yeah, all of you have noted down? All of you have noted down? Right. So thank you all. And remaining thing has been covered by the Naveen sir, that what all the strategy must be there to crack the gate examination, right? Of course, I will be there to cover the syllabus for whatever the subject they will be no, allotting me, because I have the experience of many interviews of the government as well as private, the defense, whatever the ISRO interviews and the DRDO interviews that I can share with you. See, whenever we are going to deal with the session, not only we are going to cover the numerical portion, whatever the gate portion, we are going to cover the interview part also. So that you see, cracking the gate examination is good thing. But after that, when you go enter into the interview session, like when you just attend the NPCIL interview, a BARC interview, they will not judge your gate rank, even though you have the first rank also. You got first rank, that doesn't matter there. When you don't have the fundamental thing, they will just throw you out. They will not see whether you have the good achievement. Suppose you got 90 marks or 95 marks in the gate examination, right? That will not decide your particular selection in the basically Department of Atomic Energy, DAE. So you need to be thorough with the fundamental, right? And from the starting of the lecture, from the first unit onwards, from the first slide onwards, we are going to cover the physical significance of each and every word. And at the end of the session, you will, that is my challenge, that you will be able to solve all the numericals, right? Yes or no, guys? So any doubt? Any doubt you can ask me, or we can just, leave for today. Right. So thank you all.